You see, still your body sensor, right? Still your body sensor, right? Okay. So you can see that when you stop the eating, when you feel you're no longer hungry, but how do you know that you're no longer hungry? Your sensor tells you. Well, again, your sensor is going to send the information to the brain. Okay. So I can tell you that this is going to be a complete process for the eating. And also, you can see that this is going to be a closed loop, process. Okay, starting from sensor your body situation, tell the brain, and the brain, is gonna make matching. So, hey, what kind of a situation you have? Oh, you're hungry? Okay, eat. You're bored? Oh, you're gonna eat. Okay, you're sad? You're gonna eat. However, if you should eat or not, this has to be a a pre-implemented rule. Okay. Otherwise, you're gonna miss up. So you do not know what kind of thing you need to do. Okay. So this rules has to be clear, but not everyone is the same. It's okay. Someone has the rules that if I'm hungry, I'm eating. Someone says that no, if I feel sad, I'm eating. Someone say I'm bored, I'm eating. Fine, okay. And someone say that would say that no problem. If I have one of the three situations, I will eat. Okay, it's also okay. Each one is different, but that's fine. But that rule has to be in your brain. Okay, okay. So now you can see, if I can tell you that this is going to be a perfect, control system. Will you believe that? Yes. See here, your sensor is your body. It's your feeling, right? And controller, it's your brain. And what is the law in the controller? Okay. Now I want to say that the difference controller and the control law. Okay, there's two words, and you have to be clear. Okay, control law, controller, and control law. Okay, did you see that? Okay, controller is what? Is your brain, but the control law is what? It's the rules. Can you tell the difference? You can't see it? Are you kidding me? Why? Is it a color issue? It should be. Really? Can you see it now? Yeah. Okay. Okay. Oh, so you mean is it too small? Okay. Okay. So you see, we have let me write down, continue to write. Okay. What constitute a complete control system? And apparently sensors, and apparently actuators, and apparently controllers, and apparently control laws. Can you see that? 4 components. That's all you need to form a perfect control system. Okay? Can you see that? Can you see that? Okay, good. Okay, 4 components. Okay, sensors, actuators, controllers, control laws. Okay, okay. Now, always recall the example that I've just said. Okay, that I've just mentioned for the eating. Okay, actually, based on this, once you understand this example, you can name many other examples as the control system. The control system actually exists in many different kind of areas. Okay, it's definitely existing in your human body, and a lot of tasks you perform is the results of a control system in your human body. And of course, in engineering system, there is also many control systems everywhere. Okay, so now you can see sensor, actuator, controllers, and the control laws. Okay, now see what is the purpose for this course. So you can see the 4 components, and let me tell you where you can get the knowledge of these 4 components. For example, the sensors, the physics of the sensors, actuators, and the controllers, they are not the theme of this course. Be careful. Okay, we're not a sensor course. This is not a sensor course. This is not actuator course. This is not a controllers course. Physics course. Okay, where did you get those physics of these components? Yeah, from individual sensors, right? From individual courses, right? Yeah, you can learn from. You see, for example, if you talk about the chemical sensor, then yeah, you need to study that course to what is the principle for that chemical sensors. Okay, there are specific courses for that kind. Also investigate the physics principle that the human body is subject to. Okay, so from those kind of courses, and you can understand how the sensor works. But even if we don't know the principle how the sensor works, in this course it's fine, because you know why? To me, in this course, all I need to use is that I want to know what sensors transmit to the data. Okay, that's all I need. I don't need to know how the sensor work. I only need to know the sensor send what kind of data to me. Is that fair? To say that? Okay. So if you only concern about the information that is transmitted by the sensor, actually you don't need necessary to know how the sensor works. Okay. So that is why we can still talk about the sensors in this course without mentioning the physical principle of the sensor. Okay. Okay. Same thing I can say is about the actuator. Okay. Right. And if you want to know how the actuation, work, for example, in terms of the eating, then if you really want to know how it works, then you have to investigate the muscle motion. Okay, how the muscle is going to move under the guidance, under the command of the brain, right? Okay, but to this course, I only need to know there is some mechanism perform this kind of actuating action. I don't need to know how that's exactly the principle the actuator is subject to. Okay, in other words, I only care about the behavior. I don't care about what is going to be the inside principle. Okay, it's okay if you capture the behavior, then it's good enough for this course. Okay, so again, course is not about actuators physical principle. Okay, okay. Now controller, yeah, controller, and most of the computer controller you get it from your microprocessor course. Have you guys had the microprocessor courses before so far? Oh, okay, good, yeah, good. Okay, so that course is gonna tell you how the controller's physical principle is gonna be. Okay, for example, you can talk about the CPU, you can talk about the bus, you can talk about the command bus, you can talk about data bus, you can talk about the clock, you can talk about of course, I think they were going to use Motorola's 6011 or 6012. Do they mention that? So will that teach you, the structure of that 6011 or 6012 or the DSP? Anyway, so you will get the physics principles from those courses. Okay, okay, but again, you only need to know, oh yeah, the controller performed this kind of action behavior. Okay, that's good enough for this course. Okay, then the big question is going to be, what exactly this course is going to talk about? What is left? 4 components here. What's left? Control law, right? Control law, right? So yes, this course, it's about and plus the the control 2. Okay, this 2 course, it's all about how you can develop a control laws. In other words, when you take it as granted to say, if I'm hungry, I will eat. If I'm bored, I will eat. If I'm sad, I will eat. You take it as a granted. Okay, but do you bother to ask how this rules is going to be generated? Is that right? That's a good question. Okay, it does not. You see, if you really want to know why you feel hungry, you need to eat. Oh, the physics, the laws, that you have to follow behind that, it's very profound. Will you agree with me? It's not going to be as simple as it looks like. You think this is simple just because this is your daily life, and you think this comes so naturally and take it as granted, but it is not necessarily a simple physics law. There are a lot of laws behind that. So the question is that how, if we have a control system, how we can develop such kind of laws. And that is exactly the main theme of this control 1, system 1, and the control system 2 courses to tell you. So from these 2 courses, you're going to learn a lot of methods to develop the control laws. Okay, and then you're going to learn for different kind of a target system, the physical system, and you can develop a different kind of control laws. Okay, and sometimes we just abuse the terminology, say, hey, I don't want to, every time I don't want to specifically mention, oh, I'm doing the control law development. Instead, we're going to abuse the term. It's like, okay, we're doing the control system development. Okay, you can understand it's abuse. Why? Because when we say we are developing a control system, it has to include all 4 components. Okay, and for example, we need to mention what kind of a sensor we need to use and what kind of a sensor data, how the sensor is going to transmit the data, and what kind of actuator is going to use, and how the actuator behaves, and what kind of a controller you're going to use. Okay, you use Motorola's product, you use the DSP, or even you use FPGA nowadays. nowadays, FPGA becomes, feasible too, right? And what kind of a controller you need to build into your controller to make the system work, right? So that is exactly when you say that you need to develop a control system. Okay, but because the nature of this course, we take the way to abuse the term, say, hey, we actually only concerned about how the controller is developed, is derived in this course, but we still call it we're developing the control system design. Do you understand what I mean? Will you agree with me? Okay. It's abuse of the term. Okay, it's abuse of the term. Okay, so now it's clear. And then you can mention a lot of other physical systems control system case. Okay, for example, do you have the driving experience? You have the experience to use cruise control? Do you? Yes. Okay, some answer. So can you mention that can you imitate a cruise control, like with the example that I just mentioned, the eating case? Can you imitate this two system and tell me that what kind of sensors, what kind of actuator, what kind of a controller, what kind of controllers are used in the cruise control? Do you have any idea, Samantha? Not batteries. To keep the car going. Yes. Cruise control. Speed sensor. Yes, that's correct. Okay. Speed sensor. You have a speed sensor built in the car, right? Measure the car's speed. Well, don't forget it. What do you mean by cruise control? It means that you want to keep the car driving at a fixed speed. Is that right? That's what we call the cruise control, right? Cruising speed. It's a fixed speed, target speed. Okay. Okay. So now actuator. Yeah, that's a good question. What is actuator here? Danilo? Actuator. What is going to be the actuator here? What is going to be the actuator here? TPS? Transmission system? Is that what you mean? IDK? Okay. Yeah, you gotta ask what kind of a car you drive. Okay. Before you answer that question, you need to ask what kind of a car you drive, right? Okay. Because you know why? Because the different kind of cars, internal combustion car actuator is different, and electric car actuator is different. Is that right? Okay. Right. So let's say if you drive an internal combustion car, then your actuator is what? You know what? When you are at the cruise control case, and your foot is actually away from the pedal, right? From the gas pedal and the brake pedal. So the car controls itself. But you know that when your driving speed, the speed of the cars fluctuate around the target speed. So you know what? You have a button to let you set up the target speed. Is that right? Okay. But the car is not always at that target speed. It could fluctuate around that speed. The cruise controls system, the function, the purpose is to try to keep your car at that fixed speed. How can this cruise control be done? Okay, think about this. Your speed sensor, tells there is a controller, and the controller is called a CAN. It's called a CAN controller, right? Have you guys heard about a CAN? CAN? CAN. Yeah. Controller, it's called a controller area network. It's called a controller area network. It's a kind of a control. It's a very popular controller okay, in the car, in automobile, okay? The automobile, the industry, auto industry, they like to use this kind of a controller. Put it this way, the controller area network, the CAN, it's like the Motorola's 6812, but it's much more powerful than that, okay? But by nature, it plays the same role like the 6812 in a system. It's a controller, okay? It's a controller. But how the CAN is going to work, oh, that's going to deserve another class. That's normally it's taught in the computer engineering. Like what I said, that is going to be a course about the physical principle of the CAN. That's another course. Okay, so you can learn how the CAN works, from that course. Okay, here well, it doesn't matter you use a CAN, it doesn't matter you use a DSP, it doesn't matter you use a microprocessor. And to me, I only concerned about the behavior. That is, the controller execute the control laws inside to give me the desired function. Okay, so in car, it is CAN that works. Okay, now the CAN, it's gonna, detect the speed difference, the deviation, and then decide what the car's actuator should do. You know that if you drive a gasoline car and actually you speed up or speed down the car by what? Press different pedal, right? When you need to speed up the car, you do what? You press the gas pedal, okay? When you when you need to slow down the car, you do what? You press the brake pedal. Okay, so now you can see that the gas pedal and the brake pedal are the two actuators that you can use to control the car. Okay, is that right? Does it make sense? Okay. Okay. So you have the actuator, you have the sensor, and you have the controller. So what's left is what? Is the control law. Yes, the cruise control. Yeah, there are many factors need to be considered when we build the control law. Okay, for example, in terms of the cruise control, now you definitely, when you adjust the speed, okay, when the speed deviates from the target speed, and when you adjust the speed, what do you want? Your gut feeling. Tell me your straightforward feeling. Okay, what kind of performances do you think that you want for this kind of a tuning process? Can someone, just name something? It doesn't matter. Okay, don't worry about you make mistake, you make a wrong answer. That is absolutely not a problem at all. You just need to be active on that. Okay, can someone mention, name some the design, okay, for this tuning process? What do you want? Someone, come on. So you guys did not listen to me, right? Okay. See, I cannot watch you guys, so you guys are short of monitoring. Okay? Okay. 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 So my question is this. Listen, okay? Say when you are at the cruise control and your car's velocity, the speed, deviates from the target speed. And so definitely the controller is trying to bring the speed back to the target speed. Okay, that's all we know, right? That's our experience. So for this process to bring the deviated speed back to the target speed, What kind of feelings do you think you like? Either decrease or increase, doesn't matter. Okay? It's the same thing. Okay? You want it to happen right away. Okay? Anything else, Jason? That's a good one. Any other one? What do you think? Yeah, Joseph, that's another good one. Smooth transition. You need a stable controller. Oh, come on, Abraham, you're a little bit more advanced. Okay, I'm not quite sure everyone can understand the word stable or not. Just use plain language to tell me. Safe and accurate. Yeah, Samantha, that's a good one. Shouldn't be overshoot. Chris, yeah, overshoot is also a little bit more advanced, right? Not plain. Okay. Easily disengaged. Johnny. Okay, so let me summarize what you said. You guys already mentioned, some very good, wish. Okay, let me summarize it. Okay, doesn't matter if it is advanced or if it's a plain language. Let me summarize. First, I see someone says that I want this one right away, happens right away. Okay, and the second one, and it says that I want a smooth transition. Okay, and the third one, it says that I want a stable control loop. Okay, and I have safe and accurate. I have overshoot. Okay, you see, there's so many wishes that you mentioned, right? Okay, so you know what? This depends on what kind of control laws you develop. It is not a guarantee that you put anything inside the controller, you will get this kind of a wish. Okay, for example, for example, you wanted to find happens right away. Yes, I can summarize it. You want a fast response time. That's a technical term. Is that right? Okay, but how can you guarantee that it's going to happen? Okay, second one is that I want a smooth transition. Yeah, you know what? Smooth is somehow related to the overshoot. Okay, if you have too much overshoot, you won't feel smooth. Why? Because overshoot means that you are tuning too much, go beyond the other direction, and you have to bring it back. And if your controller is not designed well, then you're going to see this kind of tuning beyond and below is going to happen back and forth, and that will cause what? Oscillation. Will you feel comfortable, smooth when the oscillation happens? Definitely not. So this is what will also depends on what kind of a controller. Okay, if you have different kind of a controller, and you will give you different kind of oscillation mode. And apparently, we want to reduce the oscillation. Is that right? Okay. Now then, let's look at it. Yeah, stable controller. You know what? I can tell you that is a very, very important wish. Okay. I can tell you right now is that every control system must be stable. If it is not stable, what does this unstable, control wheel is going to give you? Okay, for the cruise control case, if the system is not stable, then what happens? Then your speed will not come back to the fixed speed. Instead, it will go away. Either decrease to zero or go increase, to the sky. Well, of course, you can increase to the sky because you have physical system is subject to the physical limitation. However, in any case, the speed will not come back to the fixed, your desired speed in this case. Do you like that happens? Definitely not. Because when you set up the cruise control, you are expecting the car is going to go back to the, the desired speed, right? Instead of going away from that. So anything that does not come back to the fixed the desired speed, it's a failure. And that's a result of unstable control loop. So you can see that the stable control loop, it's very critical and it's very important. But it is not necessary that you put any controller inside the controller. It will automatically guarantee that the control loop is going to be stable. Okay, so this is going to be another thing that we need to do when we design the control law. Okay, and of course, the accurate, yeah, that's a very good, performance, and this one actually is also related to the oscillation. You know what? When you say your cruise control is not accurate, this means that the car speed cannot come back to the desired speed eventually. Okay? Okay? And if it does not come back to the desired speed exactly, and what happens? And the only thing could happen is the fluctuation. So oscillation is going to happen. It won't be able to keep the car in another speed. Okay. So the accuracy actually is going to be a very important factor that for the controller to guarantee. Okay. So you can see that every wish here are all related to the control laws. Okay. If I tell you that the control 1 and control 2 is supposed to tell you how you can design a good controller. Does it make sense? Okay. So I hope that you can understand from this example, you can understand what we're trying to do in this course. In other words, we're trying to design a good controller, okay, to guarantee the behaviors that the wishes that we just mentioned. Well, in this course, we're gonna call those wishes as performance. Okay, performance. Okay. We're gonna call those wishes of performance. So based on the performance requirement and expectation, we can classify the controller into good or bad. And our job in this course is to try to pick up the good controllers and avoid the bad controllers. So you have to understand how the control system works. Then you will be able to tell if a controller is good or bad. Does it make sense? Okay. So we need to understand the control system, how the control system works. Then we will be able to tell what kind of a controller is going to be good, is going to be bad. And of course, if you know which one is good, which one is bad, you don't need me to teach you how to choose. Is that right? Okay. So now I can put a summary for the purpose of this course. Enough example. I think enough example, straightforward, plain, and interpretive. And this example for the control system is that, okay, how am I going to be able to design to classify a controller is good or bad? Okay, so by the end of these two courses, and actually by the end of the first course, you should be able to tell this. Okay, you should be able to tell this already. Okay, and the control 2 is going to tell you, more ways to develop, the control laws, and so you're going to be still, around this goal. Okay, but you just know more method to develop the control laws. Okay, so by the end of this course, you ask yourself, do I know which law is control? It's better, it's good, or which control law will be bad? If your answer is yes, you get the point. If your answer is no, what happened? What happened? If your answer is no, what happened? What happened? Sebastian, failure, Abraham, that's good. You know what? You need to go back to retake the class. Do you want that? Absolutely not. So, okay. So come to the class is very important. Okay. And listen to my lecture. It's very important because we can explain a lot of things in the class. We can, talk about many examples in the class. And if you have any questions, you can ask. And if your question can be resolved on site, that will be much better than going back home to think about it. Well, you are encouraged to think about it yourself. Okay, to think yourself. You're actually not encouraged. You are required to do that. Okay, to think. Always think. Why? Why is like that? Why is like this? Okay, so if you can justify that the principles to develop a controller, and you should be fine. Okay. Okay. So any other question about this control system? Do you have any more questions? The motivation and the goal of the class. You have any questions? Good. Okay. So we're gonna, move to the okay. So yeah, I give you a quick review. Okay, I'm not gonna, talk about the introduction anymore. So I'm gonna go to the math preliminary, and absolutely we need a math for this course, and not only. Okay, Abdallah, the best way, I've just said that the best way is to come to the class. Okay, come to the class, listen to my lecture very carefully, pay attention. Okay, and then go back to think what do we talk about in the class, and then you can read the book and you can do the assignments, and it should be fun. Is that the answer to your question? You love math, Fatty? Okay, good. Okay, yeah. You have to love. Yeah, you have to love. Okay, you have no choice. Okay, you have no choice. Okay, okay. So, but don't get scared. Okay, math is it's our friend. Okay, math is our friend. Apparently, it's our friend. Don't get scared. Okay. So if you know how to play it, it's fun. Okay, but unfortunately, this course, the control course is very solid, based on the math. Okay. No, MATLAB is your calculator. Okay. And you have to know the math. Okay, Wally. Okay. Actually want you to understand math first and then use MATLAB. Do not count on MATLAB to solve your math problem. That will be the very, very bad way. You understand? Okay. Now it's just like you have a calculator. You have a calculator. Does it mean that you don't need to know how to do the addition, subtraction, multiplication, and division? See, that's the point. Okay. So, okay. Now let's look at this complex algebra. Have you guys studied the complex before? Complex number before? I'm pretty sure you had it in high school, right? Okay. Okay. So, you're gonna have the complex number. We're gonna let me go through this complex algebras quickly, and just refresh your memory. Okay. Just refresh your memory. Yeah, Michael. Yeah, you're right. And yeah. Okay. So yeah, a complex numbers and consist of two parts. One is the real part, the other part is imaginary part, right? And can somebody tell me that what does the J means? Can you tell me that J here? Imaginary number? Yeah, it's square root of -1. But what kind of role is the J plays? Yeah, yeah, Samantha, that is very good. It is the unit of imaginary numbers. Okay, impressive. Okay, and yeah, so in this sense, if I say J plays the same role as the 1 in real number, do you agree with that? Very good. You have a very bright brain. Yes. Okay. That's good. Okay. So exactly the role J plays is like the 1 in the real number. Okay. Okay. Do we need to write a 1 beside the A, the real part? No. Everybody takes it as granted because we absorb that 1. We don't need to write a 1 because actually A means that A times 1. Is that right? So in this sense, you can see that it doesn't matter real or imaginary part. They all consist of a coefficient plus a unit. Okay, period. This complex number finished, right? So once you understand, and this is a perfect for your complex numbers. Okay, now, yeah, yeah, of course, we need to calculate, define more, you know, define more quantities that are for imaginary numbers. See, you can see magnitude of the z, the complex number, is defined as the square root of a squared plus b squared. And actually, we also define the argument of the z. Okay, the argument is a phase between 0 and 2 pi, and it's calculated by this tangent inverse or the sine inverse. Okay, based on the calculated from the real and imaginary part. I'm not going to go for the details for this. This because this has been in your high school math, right? So now we can have the arithmetic, of the j. For example, j equal to square root of -1, j squared equal to -1, j cubic is equal to -j, and this is the modular number. Okay, the modular is the module is 4. It's a module of 4. Okay, every fourth powers and it come back. Okay, the j to the quad to the fourth power is going to be equal to 1, and then you come back to the j to the fifth is going to come back to the j. Okay, okay, now the polar form of a complex number. Okay, now I must tell you that this is a very important polar form. Okay, you have to understand that. Oh, you have to be very good to play this polar form, because we use a lot of polar forms in this course. Okay, so the polar form actually, it's another way to express a complex numbers. Okay, for example, here you see the complex number. I can define a, well, you can say the e to the I theta is the unit of the polar form. Okay, okay, pretty much it's the unit of the polar form. Okay, okay, just you can understand this way. Okay, see the e to the j theta, actually, be careful here. This should be the e to the j theta. Okay, not e to the I theta. Okay, because this I and j is the same thing. Okay, so e to the j theta is going to be defined as the equal to the cosine theta plus j sine theta. Why this one plays the roles of a unit? Why? You know what? Not the direction. The direction could be arbitrary, right? Theta could be in any direction. But do you realize that it doesn't matter theta, what value the theta is going to be, the direction, is going to be magnitude of this e to the j theta equal to what? Now, you see, based on this definition, it's equal to the magnitude of this e to the j theta equal to what? Based on this definition, it must be equal to the real and imaginary parts square, right? Abraham, the magnitude of the e to the j theta is 1, and that is very important. And it doesn't matter regardless of the direction. Is that right? You see, it doesn't matter what kind of value theta is going to be. Yes, the theta determines the direction of this complex number, but the magnitude always stay at 1. Okay, so that's why this e to the j theta plays the roles of like the unit in the polar form. Okay, now, so if you have the polar, you see, okay, now then, since it plays the roles of like a unit, it's very naturally to express the arbitrarily complex number in terms of r multiply e to the j theta. Does it make sense? See, you have the e to the j theta has the magnitude of 1, the unit vector. Okay, then any other vector is going to be, the difference is going to be what? Is the magnitude, is the r. Did you see that? R could be arbitrary. So this way we can correspond to between a polar form and a algebraic form. This is the polar form, and this side is going to be the algebraic form. Okay, so we can do the conversion between the algebraic form and the polar form in terms of this. Okay, so A equal to the r cosine theta, B equal to the r sine theta. You don't need me to tell you why this is like that, right? This is straightforward. Okay, so you follow this definition, it's going to be the straightforward. Okay, so now the second one. Okay, see, more about the complex number. Okay, so now you can see I can realize the conversion between the algebraic form and the polar forms very easily, right? You see, for example, here, if I have a complex number, and that is equal to the a1 plus jb1, and that is equal to the r1 e to the j theta 1. Okay, yeah, you see, this is the two form for the same complex number. And then I have another complex number, and that can be expressed as the a2 plus the jb2, and then also expressed in the polar form as the r2 multiply e to the j theta 2. Okay, fine. This are the two arbitrary complex numbers. Then we can define the summation of two complex number, which is equal to this. Multiplication of the two complex number, division of the two complex number. Now, from this, and also I can define the logarithm. Okay, logarithm arithmetic. Okay, now can you see that? You see, when I do the summation, what kind of form I use? Quickly answer my question. When I do the summation, what kind of form, express form I use? Abraham, that's not the right answer. You see, this is what kind of well, you see, I've just mentioned that this side is what form? This side is what form? Polar form is on the right hand side. Is this a polar form? See it? Is this? Can someone else answer? Ziad? Anyone? This is not a polar form, okay? You see, Zia, I can catch you. You actually did not pay attention, just now, okay? Cartesian, it's what? It's an algebraic form, okay? Algebraic form, okay? See, you did not pay attention, okay? Is that right? Did you? See here? I said this is this is the algebraic form, and this is a polar form. Okay, so you can see here when I do the summation, the right hand side is algebraic form. When I do the multiplication and the division, the right hand side I'm using is a polar form. Okay, what I want to tell you is that when you do the summation, including the subtraction, same thing for the subtraction. And algebraic form is the easy way to do it. But when you can't go to the multiplication and the division, polar form is the easy way to do it. You get it? Okay. You get it? Okay. Okay. So yeah, so in future, when you need to do different kind of, operation, and which form is going to be easy for you, okay? Summation and the subtraction, algebraic form is easier. It's convenient. When you do the multiplication and the division, and the polar form is going to be easier. Of course, you have to know the conversion between the polar form and algebraic form. You have to know that, okay? You know what? After today's class, I'm not going to come back to this complex numbers, but I'm going to use it right away, okay? Straightforward. So if you don't get it, and it's your problem, okay? Okay. So now from the complex number, we can extend to the complex function. And the complex function, we can also define the real and imaginary part. See, this time, your real and imaginary part, logarithm, well, you see, okay. So that's a very straightforward. Let's say if you write down the, let's say if you write down a plus z equal to 2 plus j3. Okay, let's say this example. Okay, see, you calculate if for this example, R1 equal to what? R1 equal to what? R1 equal to 2 square plus 3 square. So that's going to be the square root of 13. And then your log, the real part is going to be the log square root of 13. Okay. And then your theta, okay. Theta is going to be, theta is going to be how to calculate 2 plus j3 is theta. Depends on you use a tangent or use a sine. If you use a sine, and that's going to be equal to the 3 over square root of 13. Okay, so here it's going to be equal to the 3 over square root of 13 sine inverse. Okay, okay. So this is the case for the how to calculate the logarithm of the z. Just note, just be careful here. This log is based on the natural number. Okay, it's based on the e. Okay, not the 10. This is the natural base, not the 10 base. Okay, okay. So the complex functions is like this. So you define the real and imaginary part. Both in real and imaginary part, they are functions. They are real functions. Okay, they're real functions of some self, variable. Okay, and the roots of the z. Okay, now you can, because this you have a function, you have a variables, then you can define the equation. This is going to be the complex equation. So the roots of the f of z, they are called the zeros of fz. You can understand. any number, complex number, make the f of z equal to 0, we call it that is the zeros of the f of z. Okay, you have to distinguish this 0 and the number 0. This is not the number 0, okay? And the number, the complex number make f of z equal to 0 is not necessarily equal to the number 0. You got my point? Now, on the other hand, if you have the roots for the 1 over f z equal to 0, you see, I inverse, this complex function, then we call this roots is what? It's the poles of f of z, okay? It's the poles. So the inverses of zeros are the poles of f of z, okay? Okay? See, this two are the straightforward definition. You have to remember, okay? After today, I will only use the zeros, the term zeros and the poles of a complex function straightforward. And their definition is here. Okay? You got it? And okay. So yeah, this one we say the analytic, that's a math term. Okay, so you just need to know that. Okay, so now let me ask you a question. Do you understand what are the zeros of a complex function f of z? What are the poles of the complex function f of z? They are defined here. Okay, for example, I can give you example. Say f of z equal to z squared minus 1. Okay, this is a complex function. What are the zeros? What are the zeros of this complex function? Yes. Okay. Yes. Okay. Now, is there any poles for this complex function? Is there any poles? Is there any poles? No? Okay. Think about it twice. No? If you see, look at this definition. The poles has to be the complex number to make the 1 over f of z equal to 0. Now, the f of z equal to z squared minus 1. 1 over f of z is what? It's 1 over z squared minus 1. If you substitute the z equal to 0, will that give you the 0? No. Okay. Well, minus 1 plus minus 1 will give you what? This value 1 over fz equal to what? Equal to 0 or equal to what? Equal to infinity, right? Abraham? So that doesn't satisfy the condition here that we need 1 over z equal to 0. What kind of a number make 1 over z equal to 0 for f of z equal to z squared minus 1? Tell me quickly. We finish today's class. Yeah, right. Who said that? Yeah, Abraham, James, Danilo, Andre. Okay, you're good. Okay, infinity. So now you can see that for this special f of z, you know what? You do not have finite pole. Instead, you're gonna have only an infinite pole. Okay? Okay? And that also satisfies the definition. Okay, that wrap up today's class. Okay? Any questions? If you want to stay here, ask questions, I can answer. No problem. We don't need to subject to the the class time. Okay? I give you several more minutes to ask questions. Okay? Any questions? You're welcome, Johnny. No problem. Any questions? Okay. You know what? Wednesday, Ziad, Wednesday. Pay attention, Ziad. I talk about this at the beginning of the class, okay? Okay, Ziad, you need to go to the website. You got a notice of the schedule file posted, right? Okay, you should have received the email already. So you got to go to the website to check out the schedule file and then look at how, what kind of the date deadline is going to be. Okay. Okay. Any other question? No problem. Any other question? No more question? Okay. 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 I'm going to see you guys Wednesday. Okay. All right. Thank you. Bye.